I hope so. So the next the talk is the papers like is entitled with optimizing word alignments with better subword tokenization. Like it's from the University Paris-Saclay. So I'll start the video.
Hello everyone, I'm Anh-Khoa. I'm going to present the paper Optimizing Word Alignments with Better Subword Tokenization. Let's begin with word alignment. Word alignment is one of the basic tasks in natural language processing. It aims to identify translational equivalences at the level of words in parallel sentences. You can see some examples of word alignment between several sentences in English, French, Vietnamese, and Japanese in the screen. Well, word alignment has a lot of interesting and important applications. It is used to learn bilingual dictionaries, to train statistical machine translation systems, to filter out noise from translation memories or in quality estimation applications. Especially, it can also serve to explain machine translation decisions. A large number of recent researches computed alignments based on decomposition into subword units. It helps to easily accommodate open-ended vocabularies and to mitigate issues related to the alignment of unknown rare words, which has always been a challenge for discrete models. Subwords is the generation of many-to-one, one-to-many links. One-to-many links are such that a subword is linked to more than one target words, and many-to-one links is the reverse case, where a target word is linked to more than two subwords. These are difficult to handle in standard asymmetric models such as IBM1 and IBM4. They also enable to actively manipulate the length of the source and the target sentences so as to make them more even. This is a facilitative factor for alignment and translation models. Well, in that case, subword tokenization helps to control sentence length. It can be used to improve the word alignment. So now, let's describe how we do our experiments. We use the standard corpora such as arrow part, narco, time, etc. and we show the number of sentence pairs for training corpora in the left graph and test corpora in the right graph. We use the alignment error rate, F-score, precision, and recall as measures of performance. AER is based on a comparison of predicted alignment links with a human reference, including show and possible links. Note that Romanian, Japanese, and Vietnamese reference data only contain show links. In this case, AER and F-score are deterministically related. These scores are based on word level. Therefore, we need to convert subword level alignments into word level alignments. To do that, a link between a sub and a target word exists if there is at least one link alignment between the subwords. We can see an example on the bottom right of the screen. Now we observe word alignments computed by several common packages such as FastAlign, GigaPlus, FLOMAL, and SimAlign to outline some difficulties for word alignment models. As can be seen in the left graph, underlying words displayed by the red color are poorly predicted. In the right graph, the models also fail to predict many-to-one links, even with symmetrization with a large number of incorrect many-to-one links, also displayed by the red color in the graph. Another observation is that larger length differences yield more errors. This again hints at the tendency of discrete word models to generate one-to-one alignment links. Now we study the interaction between alignment and segmentation with FastAlign and FLOMAL. We perform the alignment between subword units generated by pied pair encoding PPE and the unigram method, implemented with the sentence pitch package. We independently segment sentences in each language with varying vocabulary size from 2K to 48K. With a proper choice of unit size, PB-based models are able to outperform their word-based counterparts with a gain of about 2 error points. This improvement is not clear for unigram-based models and can be seen in the left figures. Having short units on top left zones 2K or 4K on both sides yields a better recall but a much worse precision. The opposite trend, better precision, worse recall, is found in bottom right zones where we approach word-based models. For underlying works, compared with HMM and IBM4, we notice that PPE-based models are less prone to over-generate null links. As can be seen in the right figure, the best PPE models 4K, 32K remove 40 incorrectly underlined words and finds 10 correctly underlined words. For one-to-many, many-to-many links, tokens that decompose into a sequence of shorter units in the source side have more chance to align with several target tokens. However, this does not result in an increased number of correct one-to-many, many-to-many links. We collect raw subwords and plot their F scores as a function of target and source vocabulary size. We can see a large gain in F score when using a reduced vocabulary size compared with a large word-based vocabulary size. As a final experiment, we combine multiple PB-based alignment using a simple voting procedure. This method is parameterized by the required level of agreement. This is the percentage of models agreeing on alignment link and can be seen in the graph. This figure shows that considering the PB models and using an agreement level of 70% improves the F score by almost 2 points for direction German English. This means that considering multiple segmentations in alignment can be very helpful. We build on the institution that pairs of sentences with differ in length are difficult to align. As presented above, this suggests that subword splitting should be used to make the length of parallel sentences more even, which means that we try to minimize the length differences. For the global methods, we try to minimize the average length difference at the corpus level. The first one, VPM. This one simply picks the vocabulary pair that minimize the average length difference in the matrix of all vocabulary pairs that we used in the previous experiment. For VPGS, the previous solution VPM can be improved by using the following grid search procedure. We compute the average sequence length difference for a vocabulary pair based on a predefined search space radius. If we find a new vocabulary pair producing a smaller average than the current pair, we continue to explore the neighbors of this new pair. We reduce the search space radius in the case that no new pair is found. For PP-based models, our methods outperform word-based models with a gain of at least 1 point in F score. You can see that in the table on the right. This performance is close to the best results from the matrix of vocabulary pair. Unigram-based models fail to match such performance, but we still observe an improvement for research with outperforms the word-based models, F-Luman for French, German, Japanese, and Vietnamese. For the local methods, we try to separately minimize the length difference for each sentence pair. For SPM, this first method simply picks among all considered segmentations of each sentence, the one that minimizes the length difference. When there is more than one minimal segmentation, we select the one for which the total source and target length is smallest. This one only outperforms the word-based model for English, French, and English Vietnamese, and fails to achieve better F score than the global methods. For SM1, 1VP, we first collect the 10 most likely segmentations for each language using the unigram algorithm. We then select the highest probability candidate on both sides and consider the longer of the two and the anchor segmentation. We pair this segmentation with the one in the other language that is closest in the length and maximally likely. We also consider the case SM5-1VP where we include the top 5 highest probability instead of the highest one, the last step for the training data. For SSM5-1VP, this similar method extends the previous idea with more candidates without considering their likelihood probability. We sample test segmentations using the unigram algorithm for each language, then select the 5 pairs of segmentation that have the smallest length difference and use it in the training data for the word alignment. For the last one, SSM5GS, it used the same strategy as SSM5-1VP. The previous method used the optimal pair of vocabulary size computed by the research algorithm mentioned above. We should note that the last 3 methods use only one vocabulary pair. We show the performance of the sampling methods using one vocabulary pair SM1-1VP. SM5-1VP with the top 5 highest probabilities instead of 1, and SSM5-1VP similar sampling method compared with the unigram-based method assuming vocabulary size 16K. They all outperform the baseline, a fixed 16K model, and also the word-based models for French, Japanese, and Vietnamese. It also seems that including several segmentation samples for each sentence pair in the training data, using SSM5-1VP also helps to improve the performance, resulting in a simple scheme based only on length differences that consistently outperforms all other unigram-based methods. These results opens perspective for further improving these models, especially for German, Czech, and Romanian, for which the 16K setting might be suboptimal. The last method, SSM5GS, did not succeed in improving SSM5-1VP. Collusion and Outlook. We have studied the interaction between word alignment and word segmentation based on 2 algorithms, PPE and Unigram. Using smaller units notably mitigate issues with rare and underwords. Shorter units also help to retrieve more correct links for one-to-many or many-to-one alignment links. Based on the observations, we have analyzed the variation of alignment score with respect to vocabulary size. It shows that the word-based segmentation was less than optimal. We have finally explored various ways to actively optimize the Subword tokenization. Our promising results in this direction have been obtained with the unigram algorithm, owing to its ability to generate multiple high probability segmentations. We have notably found that adjusting length differences in source and target was a reasonable heuristic to progress toward better joint tokenizations, even though the relationship between length difference and alignment quality was not as clear as one may have wished, and inconsistencies have been observed between unigram and PPE. In the future, we will continue to explore inexpensive ways to identify promising segmentations and improve the alignment between Subword units. And thank you for your attention.
All right. Do we have the authors like in the participants? And if you're there, like, can you unmute yourself?
Yes, I'm here.
Okay, great. So let's see, like the chat. All right, so we have a one question from Paco. So he's asking do you have any intuitions on why smaller vocabulary sizes increases recall? Is this due to longer sequences approaching character level?
Yes, in the reference alignment, So we have a lot of one-to-many, and also we have many-to-one or one-to-many, which means that one word in SOAP language would link to more than 2 words or 3 words in the target language. So in that case, if we have a smaller vocabulary size, which means that we're gonna split more words. So in that case, we could have a longer sentence, and we could have more links, especially one-to-many or many-to-one links, and it's gonna help to improve recall. Yeah.
Thank you. Right, so do you have any other questions like from the participants, audience, or you can ask like by unmuting yourself, or like just type the questions like into the chat. So I have a question. So I think you experimented like your method like on a variety of the data set, and I am especially the Japanese native speaker, and I just wonder like how do you experiment like in that setup specifically? So so for example, like I think like in this the examples like so specifically, so the last sentence like is written in Japanese, but so they are not tokenized like in the original sentence, and like how do you manage the word level, or like so did you tokenization like before the creating the subword vocabulary in Japanese?
So first of all, basically for this data set, we already have they already split into word, and you could this is the so you could actually find the data set, and it is made in the KFTT. So basically everything is already split on word. So when using the Subword tokenization, we just split this word into the subwords. So yeah.
Okay, I got you. So the so from your experiment, so it's better to use still the subword like after the tokenize the Japanese text like beforehand, like so that is good to know to me, right? So okay. Yeah, we have another question from Paco. So the question is that in this study, you explore optimal vocabulary to improve alignment based on bilingual experiments. However, many NMT models now use multilingual vocabularies. Have you thought on expanding your study to cover the optimal segmentation when many languages are present?
Actually, well, in my study, because for each language, we have different type of alignment. So in some language, we only have one-to-one links, or in some other language, we could have more many-to-many links or one-to-many. It depends on the language pairs. So it's very interesting to have universal ways to improve the score for all of the languages. But yeah, it's interesting. Yeah.
So we have one more question from Yuri. So interesting talk, thank you. Do you have the results of a figure with F scores in a table from figures 9 and 10 in your paper? How significant are the differences?
So Okay, so for the figure 10, okay, for the figure 9, in this case, we try to compare the local methods. So it is, and we compare with one local methods is a SPM. We also shows that it is, so in this case, and for the and for the figure 10, we start with one vocabulary pair is 16K, and then when we using the sampling method based on unigram, we could, and this is the case for the three methods, SM1 1VP or SM5, and also the SSM5 1VP. So this is the difference. For the figure 10, we are based on the matrix of vocabulary pair, which means, yeah, and with many different vocabulary pairs. And for the figure 10, we only based on one vocabulary pair. Is that clear?
Well, my question was, if you just go a couple of slides back, last picture you had. Yeah, here. It is difficult to see the numbers, which the bars correspond to. So my question was, I can see that one bar is higher or lower than another, but how significant is the difference for example, English, Japanese? The blue bar and the yellow bar, what numbers do they correspond to?
Well, it's about, I think it's about like, for example, for English, Japanese, it's about 3 or 4 point F score, I think.
Okay, thank you very much.
So, yeah. So basically, we don't really see in this in all of the experiment that we have a huge improvement on the F score, but we still see that we could improve more the result. For example, in the case that for some language, when you choose the vocabulary pair being the 16K, it could be optimal. It could be a suboptimal, and if you apply these techniques, you could improve more the score.
Thank you.
So thank you for the great talk and the presentation, like Encore. So I think like we are going to have the final Q&A session, like for all the presenters, like in the remaining 10 minutes. So how does that sound, Paco?
Yeah, sounds great.
All right. So in from from now, like you can ask the questions like to the first research talk or the second talk as well. Like you are welcome to ask any questions to the authors. Can stop the share screen.
I think that's good, Akiko.
Okay, so this is the first session like I am attending like on the MT Summit. So I just wondering like how it's going on like in the extended Q&A session, but
Maybe we have more questions from people from the audience.
yeah. Yeah, we still can see like there are many attendees here. So whenever you're ready, so you can just unmute yourself and ask the questions. Like we're happy to do that.
So maybe I do have a question for Anne. I don't know, Anne, do you want to unmute your video so we can
Yeah.
say hi? If possible, if not, that's okay too. So, and related to you this question, I see, you know, for different languages, you see different tendencies, right? So for example, for certain languages, I think it was English Romanian, the word-based approach outperformed the others. Whereas in other languages, you have, you know, you have the word-based being the worst, right? So did you do a follow-up analysis? Do you have any sense of what could be causing these differences? Is it related to the languages themselves, or you know that maybe they are closer? Do you have any insights there on why we see some trends for certain languages and some other trends for other languages?
I'm not sure I quite understand your question, so.
I mean, maybe we could go back to the video. I could share. So exactly. But you know, in that graph that we went back to, that Yuri pointed out, we had word-based being the best. I think it was in blue, the blue graph being the best for many languages. And then maybe towards the end. Yeah, they're right there. So if you see, for example, English, German, you see that the word-based still beats the other approaches, or at least it looks like. It's more evident in Romanian English, right, where word-based still outperforms the others. Whereas in English, Japanese, Japanese English, English Vietnamese, Vietnamese English is clearly, the blue approach is clearly behind. So I was just wondering if you have any insights of what is this? Is this related to language family maybe, that if they're closely related?
Yeah, so I think I explained these figures because in here, CTK, all of the methods, for example, you see here SM1, 1VP, SM5, SSM5 is based on the 16K vocabulary size. Difference here that we do sampling on this vocabulary pair. So in some case, like for example, English German, it could be the suboptimal vocabulary pair. So for example, if we have 32K, we could have a better score. So, but in here, because we do the sampling, and when we do the unigram, we have to select one vocabulary pair to do the sampling. So this is the result. So in some case, we could see that, for example, English, Japanese or German English, we could see that the 16K is much better than the word-based models, and we could improve more. But in the case of, for example, here you can say that English German or German English, 16K case, it doesn't really have, it's not a good vocabulary pair. So how could we improve? Because in some case we could then try a lot of different vocabulary pair. So is there some way to improve the score? Is there some way? Is there some technique to how you say it, to prepare a good training set? Yeah. Am I clear? Or?
Maybe if you get so just for my understanding, what does word-based means here in this context, specific context? Is it not using is it based on tokenization, just regular tokenization? Maybe that's the part that I missed. I'm sorry.
Well, so so you can see here that okay, for example, so where for all of three methods in here, SM1, SM5, SM5, we use a unigram. So from using the unigram, we could sampling from one vocabulary size. We could sampling more segmentations. So I just show here that when I want to, so in this case, I will select randomly one vocabulary pair. This is the case is 16K, 16K. Okay, and then I use unigram to generate more segmentation, different segmentations. And on the three methods, I could improve the 16K. I could improve one vocabulary side pair. So, and then I will compare with the word base. So the difference here is that the 16K is not the optimal vocabulary pair for each language pair. If we select the the optimal language pair, we could have the better score. I mean, because you can see in the previous slide, you can see that most of the case we could improve the word-based alignment using the Subword tokenization.
Thank you. Yeah, that was more clear. Thank you.